Okay, so let's recall the last class. We discussed about symmetric matrices, right? So we have seen what is a symmetric matrix and a skew-symmetric matrix and its properties. So the mainly when you take any matrix, you can see that A into A transpose is always a symmetric matrix. Okay, and similarly the other way, like A transpose into A. That can you prove it? How about A transpose into A? A transpose into A, when you take whole transpose, that is same as A transpose whole transpose. So this is same as A transpose into A. So either you write A into A transpose or A transpose into A. So for any matrix A, that's going to be symmetric. So this result we proved it. And then we looked at some example. Like we started with some rectangular matrix and we saw that A into A transpose is a symmetric matrix. And another one, for any square matrix, you can prove that A plus A transpose is always symmetric. And when it comes to A minus A transpose, that is going to be skew symmetric. And with the help of these two things, we proved that any matrix can be uniquely expressed as a sum of symmetric and skew symmetric matrices. So this we proved it. And here is the proof. And then we have seen some example. Just we started with the matrix and we found out what are the symmetric and skew symmetric matrices here. And few more properties of symmetric matrices. When A and B are symmetric, you can say that A plus B and as well as A minus B are also symmetric. And AB is going to be symmetric provided A and B commute each other. Okay, when A and B are symmetric, AB need not be symmetric. If you know that they commute each other, then they are going to be symmetric. Like A into B is going to be symmetric. And similarly, if you start with a symmetric matrix A and you start with some rectangular matrix which can be multiplied with A either on the left or right, then you can prove that B transpose AB is symmetric. Similarly, okay, for other sides like B into A into B transpose is also symmetric when B is a matrix of size m by n. So power of any symmetric matrix is symmetric. That also we proved it. Yeah. So here we are at the first problem, right? So prove that a symmetric matrix of order n has at most n into n plus 1 by 2 distinct elements. Okay. So we counted this way: diagonal above entries, diagonal above and above, plus 1 diagonal, plus 2 diagonal. So we counted those entries and we concluded it is n into n plus 1 by 2. But okay, let's write the proof now. But I'd like to do it in another way. Let's say you take a symmetric matrix. Let A be a symmetric matrix. That is, you know that A transpose equal to A. And moreover, you know that if you look at ijth entry of this A transpose, that is going to be jith entry of A. Okay, so this is the relation between them. In other words, or let me write it this way: like if you take A transpose and if you look at ijth entry, that is same as the jith entry of A. Now I need to know how many elements I need to have it in this symmetric matrix. So if I know Aij, then I know what is Aj. Okay, because they must be equal. So now we'll do one thing. So we'll look at Aij when I less than or equal to j. Okay, so let us try to count how many such aij's will be there in a square matrix such that I is less than or equal to j. Once if I came to know this count, and I can come to know the rest of the entries. Why? Because I know aij will be same as aji, right? So now let me count it, how many of these elements will be there. So for counting this guy, I'll do one thing. I know from where this I and j are coming, where I comma I and j are numbers from 1, 2, 3, 4 and so on n. So I comma j, they can be any numbers between 1 and n, right? So now I'll do one thing. I'll go case by case. So when j equal to n, let's say when j equal to n, so how many choices of I you can take? So that is, if you look at a I n, so how many elements of this type are there which satisfies this condition, that is I less than or equal to n. So we can see that we have, so now this I can be any number from 1 to n. Okay, so there are n choices. So I can say that n such elements are here. Okay. So now I'd like to write it here when j equal to n. So I can say that there are n number of ain such that I less than or equal to n. That's it. Similarly, when j equal to n minus 1, so you can say that there are n minus 1 number of aij's which satisfies this condition, where now the condition is, okay, here anyway I'm assuming j is equal to n, so I'll write I less than j simply. So here also I'll write I less than j, because here in this case j equal to n minus 1, and similarly when j equal to n minus 2, the same thing. Here you're going to have n minus 2 such elements. And similarly when j equal to, let us say, 3, now you can say that there are okay, so there are 3 number of elements of this type, that is ai j. Then here also I should write j only, such that I less than or equal to j. So now if you count for all, similarly you can come to 1. So now you'll have only 1 of this kind. So when you add all of them, so now if you look at it, what are all the elements we have seen now? So if you write aij, I less than or equal to j, which exactly represents the all entries which lies on the diagonal and above the diagonal. In other words, let me tell you, when j equal to n, it means you are looking at this column, so the last column. So you came to know that in the last column there are n elements. Next, and the next one, when j equal to n minus 1, the last but one column, so it means you're just accepting one element and you're taking the rest, n minus 2. And similarly the next. Similarly here, when it comes to 1, there is only one element, next 2 elements, next 3 elements, this way. So what you can see is upper triangular matrix, like the diagonals and entries above the diagonal. So now here 1, 2, 3, 1 plus 2 plus and so on plus this. So now the total, you can count how many elements are there. So we need 1 plus 2 plus 3 plus and so on plus n. So that's going to be n into n plus 1 by 2. So if you know these n into n plus 1 by 2 entries, then you know the rest of the entries. What are the rest of the entries? How many are left? Like in a matrix, in a square matrix, total there will be n square entries. So if you want to know the other entries, how many entries are left, so you can do one thing, n square plus n by 2. So what is it? So you'll get n square minus n by 2. So if you know this n into n plus 1 by 2 entries and the other entries, like n square minus n by 2 entries, we already know it. Okay, but anyway, we can conclude that, so a symmetric matrix can at most have n into n plus 1 by 2 distinct elements or distinct numbers, whatever you say. Okay, so this is how I'd like to present the proof. You might have do it in another way, that is different, but this is the way I followed, that's it. And another way, like you can count the diagonal entries. There are n diagonal entries, and if you want to know the non-diagonal entries, that you can count it. You can count it this way, right? Let me tell you. The diagonal entries of A or n, like when you take an n by n matrix. Okay, and what are the total entries of A? Total entries of A, these are n square. Okay, so now I'd like to see what are the non-diagonal entries. So non-diagonal entries, you do one thing, you just the total elements minus this diagonal entries, that is n square minus n. But we know something about symmetric matrix. If you know that when entries above the diagonal, then we can write the entries below the diagonal. So it is enough to know half of these non-diagonal entries, not full of the non-diagonal entries. So therefore, we can say that non-diagonal entries above the diagonal are simply entries above the diagonal that I can write. Fine. So that equal to half of these entries, right? N square minus n by 2. Now if you want to know total how many entries you need, it is non-diagonal entries above the diagonal plus this n. So that will give you, that is n into n square minus n by 2. So that will give you n into n plus 1 by 2. So this is another way. So all it matters is how you count, that's it. One may count it with the help of columns like me, right? And one may count it with the help of rows, and one may count it with the help of like the diagonal and non-diagonal entries. Okay. Now here are some interesting products I'd like to introduce in the matrix product. So one is element wise multiplication. It has a name. So this is Hadamard multiplication. Okay, so if you take two matrices of same size, let's say A is a matrix of size m by n, whereas B is a matrix of size m by n. Now this product is defined this way, like A, we are going to denote with the dot circle. So this is Hadamard product is defined as A dot B, that equal to, if you look at the ijth entry of this product, so that's nothing but it's simply the product of ijth entries of A and B. This is completely different from the matrix multiplication that we have defined there. It is just element wise multiplication. Okay, and this multiplication is used when it comes to compression algorithms like JPEG or I think RGB combinations. You're going to add it, right? Or are you going to multiply there? No, I don't have much idea about it. In image compression, do you come across this element wise multiplication in matrices?
Yes, sir. Image multiplication will be there.
What?
We can do image multiplication, sir. We take two images which are of
Huh.
matrices of intensity values and we multiply them to
Yeah, we
obtain a new
multiply the
image.
corresponding entries only, right?
Yes, sir.
It's
Like
it's
this.
not
Hadamard
like the
matrix.
matrix multiplication we defined like earlier.
No, sir.
Yeah, so it means there you're following this Hadamard multiplication. Okay, it has a name. Right. So here, observe one thing, this multiplication is possible when you have matrices of equal size. You cannot multiply matrices of different size here. But in matrix multiplication, it is possible. Like if you want to multiply two matrices there, like if A is a matrix of size m by n, then B must be a matrix of size n by q. Okay. Or in other words, we can write it in different way, like A dot B, this matrix, it's going to be again m by n matrix. So here I need to take the product of Aij times Bij, where this is a matrix of size m by n, where you know what is A is nothing but Aij of size m by n, and B is a matrix Bij of size m by n. Okay, and there is another multiplication which is called Kronecker product. It looks totally different. Like the earlier element wise multiplication, you might have seen it. I don't know whether you have seen this product or not. Let me mention it. Let's say A is a matrix of size m by n and B is a matrix of size m by n. So let me write what is A equal to just a matrix Aij of size m by n, whereas B is a matrix of any other size P by Q. Okay, I don't have any condition that the rows must be equal to the columns. We don't have any such restrictions here. Now the Kronecker product of these two is defined this way, like A Kronecker product with B, it's defined like this. So first we multiply the first entry of the matrix A with the entire matrix B. It's like A11 into the other block, this entire matrix. Similarly, A12 into entire block and A13 into the entire block this way. So when you look at the size of this matrix, similarly here you are going to have A21 into this block, the entire B, this I mean B, okay. So here I have m rows and n columns, and here I have m rows and n columns, and so how many of them are there? So if you look at the number of columns, how many columns are there? So I said this is a matrix of size m by n. So in A there are n columns, and in B there are q columns. So n is appeared for q times. How many?
MP by N.
Yeah, so there are nq columns. Similarly, if you look at rows, there will be mp rows. So you'll get a big matrix. So let me write it. Now this is A cross B is defined this way. A11 into the matrix B. Similarly, A12 into B, and so on. A1n into B. This is the first row. The second row is A21 into B. This is A22 into B, and so on. A2n into B. So when it comes to the last, AM1B, AM2B, and so on, AMNB. Okay, so this is a matrix of size MP by NQ. And sometimes we need to deal with multi-dimensional matrices. They have a name. They were called tensors. Multi-dimensional matrices. It means here in a matrix you are seeing entries as real numbers, but there in tensors the entries itself are matrices. For example, I'll write one such example here. So A, B, C, D. So this is a matrix of matrices. So if you look at the first entry, that is 1, 2, 5, 1. This is 3, 1, 2, 6. And here 1. Like similarly you write a few more matrices here. That's it. Okay. So if you want to visualize this, like if you want to know the dimension of this guy, it's 2 by 2 of, and then 2. Yeah. So earlier you're in a plane, now you move to a space. It's like to visualize this matrix, I think you need to go for R3, because there are 3 dimensions I'm going to have. Okay, anyway, we'll discuss later on what are these tensors and all. Okay, so maybe once if we are done with this course, if we have time, then I'll discuss about it. Okay. So this Kronecker product, it will be useful when it comes to the multidimensional matrices. There you can see more uses of this. Okay. And we need to discuss the few properties related to this Kronecker product. That I'll discuss later on. Okay. So now I'd like to discuss about Hermitian matrices. We have seen what are symmetric and skew-symmetric matrices. Now let us see what are Hermitian and skew-Hermitian matrices. So there's a small introduction I'd like to show, like when this topic was developed. Similarly, you can see that when A is a square matrix, A minus A star, so that's going to be skew-Hermitian matrix. Okay, you can see these proofs clearly, like the same technique, A, B, like you take just star of it and you can find it as same thing. And the next thing, let's say if you have A, this is a Hermitian matrix. And you start with any matrix of size m by n. Okay, then you can prove that B into like A into B star. So this is a Hermitian matrix. Since we have proved all these results there, so I'm not going to do it here. And what are the other properties we have seen? We discussed about these properties, no? Like when if A and B are, let's say if A and B are Hermitian, let's say A is a matrix of size m by m and this is also a matrix of size m by m, then what can you say about their sum and their multiplication and all? So the sum is going to be Hermitian, there is no doubt in it. But when it comes to the product A to B, so this is going to be a Hermitian matrix provided, let's see, AB whole star, we know this is same as B star A star, and you know that since B is Hermitian, we can write it as B, and A is Hermitian, so we can write it as A star as A. So that's equal to B, but we want this to be equal to AB. So therefore, we can say that this AB is Hermitian if AB equal to BA. Okay, let me do one thing. Let me write some examples for a Hermitian matrix. Let's say A equal to here I am allowed to write any element. Let me take 1 plus 2i. Can I have a Hermitian matrix where you have this entry? We want A star equal to A. It means when you take conjugate, that must be equal to this. So here you'll have only real entries. Let me write a 2 by 2 matrix. So 1, and let me take 1 minus here 1 plus I. So you can see conjugate, that is same as 1 minus I, 1 plus I, conjugate, 2 conjugate. So this 1 1 plus I, this is 1 and this is 2. Now I need to transpose A transpose, that's what A is. That will be 1 plus I, this is 1 plus I, yeah, this is same as A. Okay, so you see that the diagonal entries must be real. Say Hermits, this is what we want, A whole conjugate, that must be equal to AJ. This is what you expect. So when A equal to J, and I equal to like, so this is AII equal to HH, AII. So you need to take one Z conjugate equal to Z. That implies Z must be real, isn't it? I mean, when x plus iy whole conjugate equal to xiy, means your I is equal to iy. These two that y equal to minus is possible when y equal to 0. It means this Z must be real. So you can see that diagonal entries must be. Now let's try to write 3 by 3 Hermitian matrix. Let's say A equal to, we know the diagonal entries must be real. Let me write some 1, 2, and where you write 1 plus and you should I. What do you write it here? It's conjugate. And minus I, then it's get 2 plus I. Here 5 plus 3 conjugate 5 minus. So you can see that for this matrix A is equal to, so this is an example for a Hermitian matrix. And let us do Hermitian matrix. Now how about Skew-Hermitian? And one more thing you can observe about this Hermitian matrix, like this one, A, since it is complex, it is true for thing. You write it as m plus. But the interesting part is m is going to be symmetric and n is going to be skew symmetric. Okay, let me discuss this first, and later I'll move to skew symmetric matrix. So if you take a symmetric Hermitian matrix, sorry, I'm saying symmetric, it should be Hermitian. Let A be a Hermitian matrix. Then, like A can be expressed as m plus I times n. Okay, so you know one thing, when you take, since it is Hermitian, you know that A star equal to A, so that is nothing but m plus in whole star. M is a symmetric matrix, and n is a skew symmetric matrix. Okay. So every Hermitian matrix can be expressed as m plus in, where m is a symmetric matrix and n is a skew-Hermitian matrix, skew-symmetric matrix. Okay. A Hermitian matrix, you just give me a symmetric matrix and a skew-symmetric matrix. With that, I can simply write Hermitian matrix. Okay. Next. Now let us discuss about skew-Hermitian matrices. So let's write an example for it. We already discussed, but I'd like to write an example for this. So the example is, let's say A equal to, see, we want A star equal to minus A. So when it comes to the diagonal entries, like AII, so even though when you take transpose, the diagonal entries remain same, AII, and we want the conjugate equal to minus of this. It means when you take x plus iy, when you take its conjugate, and we want this to be equal to minus of x plus iy. So now let me see. So this must be x minus iy, whereas this is minus x minus iy. So when you compare this, x equal to minus x, so it means x must be 0. There is no other alternative. And yeah, there is no problem with y. Minus y equal to minus y, no issue. Okay, so when it comes to the diagonal entries, they must be purely imaginary. So when you take a skew-Hermitian matrix, the diagonal entries must be purely imaginary numbers. Similarly, when you take a Hermitian matrix, the diagonal entries must be real entries. So let me take purely imaginary entries like I, 2i, minus I. And next, how about the other entries? So if I write 2 plus I, so here we want Aij whole conjugate, that we want it to equal to like Aji, minus of Aji, sorry. So you take conjugate and multiply with minus. So when you take conjugate, it is 2 minus I. When you multiply with minus, you'll get minus 2 plus I. And here, let me take 3 minus I, conjugate and multiply with minus, so minus 3 minus I. And here let me take minus 5 plus I, so take conjugate and multiply with it, that is 5 plus I. Can you see that it is a skew-Hermitian matrix? So if you have doubt, let's check it. First let me take its conjugate. So conjugate of this matrix is minus I, 2 minus I, 3 plus I, minus 2 minus I, minus 2I, and minus 5 minus I, this is minus 3 plus I, 5 minus I, and I. Okay, I take conjugate. Now let me take transpose, that is A star, which is A conjugate whole transpose. So when I take conjugate, transpose, this is I, this is 2 minus I, whereas this one is 3 plus I, and here Now this is minus 2 minus I, whereas minus 2I 5 minus I, and here this is minus 3 plus I, and this is 5 minus I and I. So let me take minus out. I think 5 minutes. So when I take minus out, sorry. So this is I, and when you take minus common here, you'll get 2 plus I, whereas 3 minus I, and this is minus 2 plus I, and this is 2I minus 5 plus I, and how about this? Minus 3 minus I, because I'm taking minus out. So this is 5 plus I, and this is minus I. So is it same as I mean I 2I minus I? Yeah. So this equal to minus A. So you can see that, you can observe that, therefore A star, which is same as minus A. Therefore it is a skew-Hermitian matrix. So in a Hermitian matrix, the diagonal entries must be purely real numbers, whereas in a skew-Hermitian matrix, the diagonal entries are purely imaginary numbers. But when it comes to skew-symmetric matrices, there the diagonal entries must be 0, because there you are taking real entries, so there is no question of imaginary. So that's why there the diagonal entries are 0 for a skew-symmetric matrix. Okay, so you do one thing, you take it as an exercise, you try to construct 3 by 3 symmetric matrices, Hermitian matrices and skew-Hermitian matrices. Not only just 3 by 3, 4 by 4 as well. So this is your homework. So first, this thing you need to prove, AB whole conjugate is A conjugate, and then other thing is this, construct 3 by 3 Hermitian matrices.